Hey, what's up, guys? This is Cheng here. So today, LeetCode problem number 1782. Count pairs of nodes. Okay, so you're given like an undirected graph here, represented by integer n, which is the number of nodes, and then you are also given like the edges list, right? So I think this is very common for graph problems, right? And then you're also given like an integer of queries, integer array of queries. So the answer for each of the query is the number of pairs of nodes, pair of nodes A and B, and satisfy the following conditions. So the first one is that A has to be smaller than B. Second one is that count is strictly greater than this value, where count is the number of edges incident to A or B. Basically, it's a union of A and B, the incidence of A and B, and return this answer right here. And there could be a basically duplicated edges between two nodes. Okay. So first, so what is the edges incidence, right? So for example, we have this kind of the example one here. So we have 4 nodes, and then we have like 5 edges, right? So if I draw this graph real quick, so we have 1 here, we have 2, 3, and 4, right? So between 1 and 2, we have 1 edge. When we have 2, 4, and then we have 1, 3, we have 2, 3, and then we have 2, 1. Basically, there's another edge between 1 and 2. Okay, and here we have this kind of number of edges incidents for each pair. Okay, so for pair 1 and 2, right? So how many edges? Basically, the incident of the edge, the incident of the pair, the edges incident for the pairs means any edge that connects to any of the nodes here. So in total we have 5. In total we have 5 edges here, right? And as you guys can see here, so for 1 and 2, all 5 edges, they're all connected to either 1 or 2, right? Because there are like 3 edges connected to 1. There are like how many? 4 edges connected to 2, right? But there are like 2 duplicated edges. That's why, the answer, that's why the incidence of edges for pair 1 and 2 is 5. And then another one, 1, 3 is 4. Why? Because we have 1, 2, 3, 4 edges connecting to 1 and 3. Only this one doesn't connect to either 1 or 3, right? So on and so forth. So we have 1, 4 is also 4 because this edge, the edge between 2 and 3 doesn't connect to either 1 or 4. That's why we have this 4 here. Okay, and it asks us to find the number of pairs, right, that satisfy this current query given this number. That's why, for if you're given 2 here, so all the pairs, right? All the pairs basically, are greater than 2. That's why we have 3 here. That's why we have 6 here. And then for 3 here, we have 1, 2, 3, 4, 5. We have 5 pairs who is greater than 3. That's why we have 5 here. Okay. And then the constraints here, right? So we have constraints. The query is pretty small. We can just simply ignore this. Only 20 queries, but the edges and the nodes are like 10 to the power of 5, right? Cool. So, to solve this problem, I think first thing we need to figure out is that how can we calculate this this count, right? That's the first thing we want to figure out. So, like I said, we have 1, 2. Maybe I shouldn't have removed this one. So we have this one, right? That's the graph here. So given like the edges, how can we calculate given like a pair of nodes, how can we calculate the count? So the way we calculate is, if we have a degree, right? So if we have a degree of each node. So for 1, what is the degree for 1? It's 4, right? Sorry, it's 3. Okay. And how about the degree for 2? It's 4, right? Because there are 4 edges connecting to 2. And 3 is what? 3 we have 2, 4 we have 1. Okay, and given like any nodes, given like any pair of nodes, so the way we calculate count is that we use the degree of degree, right? Degree u plus degree v, right? Minus what? Minus the edge count. The edge count between the u and the v, right? So for example, we have 1 and 2 here. So degree 1 plus degree 2, we have 7. And 7 minus what? Minus 2, because we have 2 edges between 1 and 2. That because this is, when we calculate this one, we double counting, right? We double counting these things here. We double counting the degrees. This one will equal to count, right? So which means that first we have to process the edges, right? And then for each of the node, we'll calculate its degrees separately, and then we're also going to maintain like edge count for any pair of the nodes here. So remember here, we only maintain like 1 and 2, not 2 and 1 here, right? Because the 1 and 2 and 2 and 1, they are actually the same, right? And we don't want to redo the work, because saving 1 and 2, it can represent 2 and 1, because the node itself, the pair doesn't have a sequence, right? So and here this condition here, a is smaller than b. So this one simply means that given like a pair, the pairs, we only count these 2 nodes once, right? Because for 1, 2 and 2 and 1, right? 1, 2 and 2 and 1, those 2 pairs, obviously the count will be exactly the same, right? But the answer is that we only count these pairs once, right? Because we don't count this 2 and 1. That's what this a smaller than b is telling us. So yeah, and yeah, so basically, so first we figure out how to calculate this count, and then with this kind of formula, given like 2 pairs, we can know, okay, so if this pair is a candidate, right? It's part of the count. Okay, then the next question is that how can we solve this kind of queries? Given like these edges and nodes are very big here, a brute force solution is that we simply loop through the entire. We do a n square loop to find all the pairs. Okay, and for each pair we use this formula to calculate the count, and then we compare with the values in this query here. But obviously, as you can see, this is O of n squared time complexity to find all the pairs in the for this graph, right? And that obviously will TLE, and that's what makes this problem a hard one, right? So yep. So, and how can we solve this problem, right? So if we take a go back to this formula here, we see that okay, we have degree u plus degree v here, right? And then we do a minus this edge count, and then we compare this one with the query value here, right? If we only take a look at this one, degree u plus degree v. Okay, so if we don't consider that edge count between u and v at the moment, if we only want to check if this one is greater than the value in the current query, can we quickly calculate the basically the count, right? The total counts of pair, the pair counts that we need for the current query. So the answer is yes. So how can we do it? Basically, we're going to sort. We're going to sort this degree here. So what does it mean? It means that, after sorting, so we're gonna have like a degree representing something like this. So obviously we're gonna have like 0. We could have like a 0 degree, because let's say there's no edge connecting to that uh, uh, node at all, because it's not guaranteeing this graph is they're all connected, right? So we could have like a node have a 0 degree here. So let's say we have a few zeros, and then let's say we have 1, 1, 2, 3, 4, 6, 7, 8, 10, right? After sortings, we could have like a degree in this format, right? So what we can do here is that, basically this one represents the degree, right? For each of the nodes here, we can use like a 2-pointer technique. So let's say the left will be pointing to here at the beginning, and then the right will be pointing to here. So for each of the u, okay, let's assuming we iterate this u first, right? For each of the u here, starting from here, right? So if we have the u here, and then we can try to shrink, move this right pointer to the left, until this condition doesn't match, right? So let's say we for this left pointers here, we move this right pointer to here, okay? So it means that uh, on the right side, everything here is greater than the value, but if you keep moving to the left, then this one does not hold. So what does this mean? It means that, how many pairs we have find for this given like u equals to the first element. We have 4, right? Then we have a count. So we have 4 here because we have 1, 2, 3, 4. 4 pairs that can satisfy this above condition, right? And then, okay, so we keep this right here, move the right pointer here, and then we move the left pointer to here. Okay, and then basically for each of the left pointers, we try to shrink this try to move this right pointer to the left as much as possible. And also, since the left pointers, this degree u will always be increasing, right? So, and this will always increasing. It means that, there's no need to move this right pointer back to the right. There's no need to do that, because it can only possible that we can keep moving this right pointer to the left, right? Because since this one, this degree u is always increasing, right? Which means that, the this degree v here could be decreasing, right? And every time, since every time we have like a new degree u here, we can try to shrink this one, and then every time, let's say we at 0, obviously, we cannot move this one to the left, this right pointer to the left. That's why we have another 4 here, right? So let's say we have yeah, maybe this is not a very good example. Let's say, for example, we have this kind of 1, maybe 1 here. 1 is probably also 4 here, and then we another 4 here. But when we are at 2 here, right? Let's say this is the left here. Now we can move this right pointer to here. Let's say, right? Then we can plus 5 here, because with this 2 here, we're saying that, we have find like another one more pairs that can satisfy this condition. That's why, we can simply use the n minus the right pointer to give us the result, right? As you guys can see, so in this way, we only need to use like O of n time to calculate all the possible pairs, right? For this u and v, as long as they're sorted. And another like the like special case is like this. So let's say if the left is equal to right, right? So let's say the left keeps moving to the right, and eventually the left pointer will meet the right pointer, right? So let's say the left and the right, they're here. They're all pointing to 4 here. So what does this one mean? It means that anything on the right side will be satisfying, will satisfy this condition. Okay, so in this case, we don't have to use this right pointer anymore, because we already know that the left pointer, anything on the right side, they are already satisfying the condition. So we can simply use the n minus left minus 1 to calculate the how many more pairs for this current u here, because the pairs that we are getting here is the entire elements on the right side of the current left pointer. That's why we can use n minus left minus 1, right? So yep, and so that's how we use the two-pointer technique to quickly calculate the total pairs, right, of the nodes that satisfy this condition. And one more thing, so and because here we are not considering the which one is bigger, right? So because here the left and right, since we sorted by the degree, so it's not guaranteed that so the u is always smaller than v. It's not guaranteed because we sort by the degrees, not the values, right? But that's fine because, like I said, even though let's say u is greater than v here, but since we're using two pointers here, we can always switch the u and the v, right? So that will also we can always get that, right? So let's say for the count 1 here, the node is 7, right? And then for another count, we have 6 here. So for 6, let's say the count is the node is 2 for the count 6. So let's say these two pairs satisfy this one. So it's fine, right? Because 7 2 and 2 7, they're the same. We can always switch that. So it doesn't really matter the basically the value of the node in this case. All we care is the degree counts, and then that's how we use the two pointer at least to calculate the pairs for this condition, right? And that's the first step, right? So with this kind of conditions, we are basically we're overcounting the pairs, right? Because we haven't taken into the take the edge count between these two nodes into a consideration, right? We haven't taken into this one into account. So which means that after this one, we have to do some adjustment, okay? And so how can we do the adjustment here, right? We only need to loop this edge count, right? Remember, so we already have this edge count, right, pre-processed. We only need to make basically to loop through this edge count, and then for this edge count, the key is the u and the v. It's a pair u and v, right? And for each of the edge count here, we just need to check, first if this degree of this u and v is greater than this v, right? And then also we also need to check if this degree u plus degree v minus this edge count it's equal smaller than this value, right? Only then we know we know that we need to decrease our count by 1 for each of the element that satisfy both of the conditions. And so the reason being is that so first we only need to care about we only need to care the pairs in this edge count, because only an edge could affect only the pair of two nodes who has like a common edge that could potentially affect our final counting, right? because if let's say if the u and v doesn't even have like a common edge, basically this thing, right? The degrees u and v plus greater than value will be correct, right? Because only when this edge count has a value, right? Then that's when we need to check if this pair, if this edge count could affect our final answer. Yep. So and maybe I'll try to I'll start coding here, and then maybe along the way I'll explain a little bit more about the last adjustment step here. So we're gonna have like a few things here. So for degree here, I'm going to use like a 0, 1 plus n plus 1. So the reason being, I use the degree allocate everything for all the nodes is because even for the degree for the node has 0 degrees, we still want to it's still part of our answer, right? And then we do n plus 1 because the edges, right? It's 1 based. It's not 0 based. That's why we have to do n plus 1 here. And then I'm going to have like the edge count, right? Edge count for any between any nodes. And then we're gonna have a u and v here, in edges, right? So we're gonna build that, right? Degree u of u increased by 1, and degree v is gonna increase by 1. And then for the edge count, I'm going to use this one. So if u is greater than v here, I just swap u and v and vu, right? And then I do this edge count of u and v increased by 1, right? So now we have all the informations we need here. And then so another one is that we also want to sort the degrees here, right? So which means I'm going to have like a sorted degree here. Sorted degree going to be the sorted of the degree starting from 1, right? Because the 0 is not useful, right? Only 1 to n is useful to us. And now we have the answer. So the answer will be empty at the beginning, and then for each of the value, right, in the queries, so we have a count, right? So the count will be n. So like I said, we need 2 pointers. We have a left, right's going to be n, right? Starting with n, and then for left, I'm going to enumerate, loop through the L, right, from 0 to n minus 1, right? So because we need at least 2 nodes, right? So we have this kind of sorted like degrees here. The left nodes, the left nodes has to stop here because it needs another nodes, right? That's why we stop at n minus 2 here. And then I would basically try to shrink, right? Try to shrink the right pointers as much as possible. So, and I do this. So while the right minus left is greater than L, and the sorted degree, right, of L plus sorted degree of R is greater. It's R minus 1 is greater than value. Okay, then we do a R minus, do this. Right, so here I'm doing this run because I only shrink this one when the R is still greater than L, right? Otherwise, I think this is 1. Yeah. Otherwise, there's no need to shrink, right? Because in that case, we're going to the second condition here, right? So, and here, if L is smaller than R, right, then it means that we have to use the R to get the count n minus R, right? Else means what? Else means that we have n minus L minus 1. right? So because again, right? So let me repeat what I'm talking about here, right? So we have L and right here. This is the time. If L is here and R is here, then we know, okay, so we have two pairs for this L here, right? Because L cannot move to here. But if if L has reached to R here, so if the L has reached to R here, it means that we shouldn't we don't have to use R here, because anything on the right side of the L is gonna will satisfy the condition. That's why we use the n minus L minus 1, right, to calculate the valid pairs for the current L, right? And then the next step is that we're gonna adjust, right? Remove invalid pairs, right? So to remove the invalid pairs, like I said, only the pairs who has a common edge could potentially affect the count here. That's why we can simply use the edge count, to do the adjustment, right? So the first condition is that if the if the value, right, if the degree, right, degree u plus the degree v is greater than value, right? So we do this one because we check this one to make sure this u and v is part of the count, right? Because if this one is smaller than value, the count will not include this pair at all, right? So that's why first we need to check, okay, if we have count this pair before, right? And then the second one is that we have to take this edge count into the consideration. Basically, if the degree u plus the degree v, right, minus the edge count of u and v is equal or smaller than the value, right? Then we do what? We do a count minus 1, right? So here basically we're completing we're completing this formula here by subtracting the common edges, right, between this u and v. If this one doesn't satisfy the query value here, basically we remove it from the count, right? And now we have the correct answer for this query. So we can simply do this append dot count, right? And then we return the answer in the end. Cool. So let's try to run the code here. Okay, accept it, and yeah, so it passed, right? Yeah, I mean, so the time complexity for this one is what? Actually, it has to be the sorting here, right? Basically, it's a degree of the edges, basically, right? No, sorry, it's a degree of it's the total number of the edges of the nodes who has the degree, right? So I would say it's an n log n here. So the worst case scenario, right? So we have n log n to sort this one. Yeah, and all this one here, it's just like a for loop here, right? So the for loop here, since we're using 2-pointer here, so it's going to be O of n here. That's why the total time complexity is going to be n log n. That's bounded by this sorting here. Yeah, I think that's pretty much right for this problem. Basically we calculate the degree first, right? And then since we count this pairs separately by only considering this degrees for u and v, right? So that we can use like the 2-pointer technique after sorting the degrees here, right? To quickly calculate the total pairs. And then later on in the end, we we try to remove the pairs that it's invalid, right? By doing this kind of thing. It's a little bit tricky to think about. I agree. This one is a pretty difficult problem, you know. Yeah, I think I'll just stop here anyway. So thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.